Thanks so much, Gabriel and Jean, for inviting me to this. It is really a pleasure to be here. This is a fantastic location, a fantastic place, a fantastic person that we're celebrating, so thank you. I'm going to say, well, you see my title, but let me just say a few words about my journey with Stefan. I feel like I've been trying to catch up to Stefan for 35 years. It's not 45, Johan. You need a little bit of arithmetic, rehabilitation. So 35 years. I was a master's student at MIT with Ted Adelson in the late 80s. And I was building, my master's thesis is actually on orthogonal subband transforms. And they were cascaded, so they were actually multi-scale. And I had been, and Ted, of course, was the developer of the Laplacian pyramid with Peter Burt. So this kind of concept of cascading and building representations was something he had been excited about. So I started working with him, and that's when I first heard about Stefan, and who was writing his PhD thesis at Penn in the GRASP laboratory, as you already heard. And by the time I finished my PhD, I moved to Penn and took a faculty job in the GRASP lab, but Stefan had already left. He was already at NYU in the Courant Institute. 3 years later, I made another attempt, and I moved to NYU, but Stefan had already left and come to Paris. So I've been at NYU stuck ever since, wishing that Stefan would come back. And now, 35 years later, I'm the director of the Center for Computational Neuroscience at the Flatiron Institute and the Simons Foundation. And Stefan is a regular visitor to the Flatiron, so we finally have our chance to spend a little bit of time and actually have started a collaboration. So I will talk about that at the end of my talk. But first, let me kind of get you toward that. So my work is, I study vision. I'm interested in visual representations, analysis of images, and I do that, I'm interested in both the biological side of that, how do we do that in our brains, the perceptual side of that, but also signal processing and image processing, and really the fundamentals of what it means to take in light, process it, represent it, and understand it. And so, at the core of this, really, since I was a graduate student, is this notion of probabilities and prior probabilities on images. I was interested really as a master's student. I started thinking about what does it mean to describe images probabilistically or statistically? How do we capture these things, and how do we then make use of that? How does the brain make use of that? And of course, in modern times, that has become more of a question of how do we learn those things. But the starting point really is what's on the slide here in very brief form, in a nutshell. The history of this field goes back to I'd say the 50s, really earlier, in building Fourier models and spectral models. And that's kind of the classic model for images. It's what you find in textbooks on image processing, on signal processing, the idea that you should assume translation invariance, you assume Gaussian model statistics, and describe the covariance structure with the translation invariance, and then you get to spectral models in the Fourier domain. In the 90s, we had this revolution that Stefan played a major role in, which is the idea that when you use localized filters, bandpass filters, oriented filters in the image domain, you can build the new kinds of models because the distributions are highly non-Gaussian. And it was a very strange thing when this first emerged, the idea that if you did a linear process, a convolution, and looked at the statistical properties of what came out, you saw something non-Gaussian. It shouldn't be true. If the world was Gaussian, every way you slice it, you should get Gaussians, certainly with linear processing. And so a convolution shouldn't be yielding something non-Gaussian. It must have been something surprising and magic. And in those days, people were very excited about this notion. And that led to a whole set of models, unions of subspaces, independent components analysis, lots of different ways of slicing and dicing those concepts and thinking about how to build and use those models in image processing, also to use them to understand something about the brain. So again, the interactions between sort of the signal processing community and the neuroscience and perception communities were, these are not new things. They've been going on really for, since the beginning of these fields. Inspirations and ideas trading back and forth. And in the aughts, I guess we say, we went forward from those sparse models to joint sparse models. In my group, we developed Gaussian scale mixtures with Martin Wainwright and Javier Portilla, and we used those for denoising and texture synthesis and compression, all kinds of things like that, just to understand what we could do with those. And also, we used the same models and the same ideas to describe what was happening in visual cortex. So this is kind of a little bit connection to Shihab's talk. I'm not going to talk about the biology at all today. I'm going to just focus on priors. And also related, there were a whole set of very beautiful algorithms and concepts about using SVD and higher over-complete representations to understand how to build adaptive bases. And Mickey Elad, who's here and will talk, I guess, tomorrow, did a lot of work on that along with Freddie Brookstein and other people in the room. So, so we have all of this happening through the aughts, and I think we kind of hit a wall because these ideas were very beautiful, but it became very difficult to keep constructing them, and building on them, basically by hand, by making observations, low-dimensional observations, and asking what's going on, in what ways is this not Gaussian, in what ways can we describe these probabilities, these statistics that we're observing, and how do we continue to build out, of course, with a goal of building descriptions of very, very high-dimensional spaces, images, typically, for my work at least. So, and a lot of these things get tested not by sampling, certainly not back in those days, but by using them to solve inverse problems. And the simplest, probably, of all inverse problems is the denoising problem. So I'm just going to pop this up quickly. You all know this, so I'm not going to belabor it. But you have an image, you have a noisy observation, and then you have to remove the noise. The joke with there's some pepper and there's a vacuum cleaner. And the standard, if you want to minimize squared error, the way you do this is you estimate the posterior, the mean of the posterior, right? So here's the estimate. You're trying to minimize the squared error in expectation. So you integrate this against the probability, the conditional density of x given y. That is the original given the observed noisy. And the answer to this problem is very easily derived. It's just the mean of the posterior. Okay, so we want to compute the mean of the posterior of some density, but to do that, we're going to have to say what the density is, and in particular, that at least the conventional thinking is that in order to do this, you need to know the prior, and you need to know your measurement model. And you're going to put those together and calculate this integral, and that's going to give you your answer, or you're going to approximate that somehow. Okay. And of course, that's what gives us the Wiener filter, which is really classic in all the textbooks. Just basically do a Fourier transform, and within the Fourier domain, multiply each frequency by a constant, which is appropriate given the signal-to-noise ratio in that particular frequency. Images have spectra that fall. The noise is flat. So the ratio of signal-to-noise changes for different frequencies, and you multiply it by an appropriate constant. And I think most of you know that. I'm just giving it to you in loose terms. But the same sort of structure can be used now in the sparse situation. And Stefan had proposed, I think in his '89 paper, this as a description of the densities, that the densities are much more peaky than a Gaussian, and they have longer tails. You can capture them with a stretched exponential or a generalized Gaussian, where beta is something like, I don't know, 0.7, something like that, less than 1. So the point is that if you assume this, then your estimates, your conditional mean estimates, are no longer linear. And that was a little bit shocking back at the time. I think people just assumed that if you have Gaussian noise and you're minimizing squared error, the answer must be linear. It's not. The answer looks something like these things. You get these sort of thresholding-like functions, nonlinear functions that basically suppress low amplitude coefficients. Okay, so there we are. We're trying to build up ideas of priors. We're using them and testing them by seeing how well they work in denoising. The progress is good. By the time we get to the aughts, the joint models are working much better than any of these kinds of models. But all of these models are operating by doing some sort of transform, typically a linear transform, then doing some processing on the probabilities, and then transforming back, as you can see in this diagram. Okay, so then we get to, I don't know, 2013, 2014, and everything changes. Because now all of a sudden, people jump in with deep nets, and as most of you know, deep nets provide these architectures that are based on convolution, so there's something familiar. They're based on rectifiers, that's also somewhat familiar. But they do things that we didn't think were possible. So you chain these things, you train them. This is an example, this is a 2017 example. 20 layers of these things with 64 channels in each layer. It's very straightforward, the architecture. Convolutions with 3x3 filters, batch normalization and rectifiers. 700,000 parameters-ish, which sounds completely insane. If you said to somebody in 2010, I'm going to build a model with 700,000 parameters and I'm going to train it to do this problem, you would have said, you're crazy, that's never going to work. So here it is, it works, and we all know this now, and we're all, maybe we're not shocked by it anymore. Though the older you are, the more shocked you are by this, and maybe you're still shocked. If you're younger, you think, yeah, that's how it works. So yes, that's how it works. And you get out of this, you train this thing on a big data set, and you get state-of-the-art performance that just blows everything else out of the water. And it blows it out of the water not just in terms of mean squared error, but visually. And so for those of us that are interested in perception, this is also shocking. The results are sharp, crisp, like nothing we've ever seen before in any previous results. So, but nobody knows how it works. Nobody really understands what's inside that network and how it is that it's achieving that. Another thing, one little comment, is that you can train these things to be universal. So you throw one of these, you can teach this thing, this network, to operate for any noise level without being told what the noise level is. So you hand it an image and it'll remove the noise. You hand it a really noisy image, it'll remove the noise. Hand it a very slightly noisy image, it'll remove the noise. So it's really quite remarkable, a very flexible and powerful solution that we don't completely understand. They're trained using basically regression. So you take lots of pairs of noisy images and their original counterparts, and you just train this nonlinear thing to do the mapping. Okay. So now the frustrating thing is, inside of that box is a prior, because at least in my way of thinking, inside of your brain is a prior. You know what images are supposed to look like. If I show you an image that's corrupted in some way, you notice it right away. We all notice it. How do we know? What is it that tells you what part is the corruption and what part is the part that's supposed to be there? Well, you're used to looking at images. You've seen a lot of them. Your brain has figured out how to do this, and it knows what's real and what's not. Or at least it's suspicious about things that are real or not real. So this network is achieving something similar, but we don't know how. And the question then becomes, how do we go about pulling the prior out of this? So this thing has an implicit prior inside the network. It's not really a prior. It's not computing a scalar function on the space of images, a probability. It's a mapping that maps one image to another image, but it is using a prior somehow implicitly. So the question is, how do we get that? How do we access the prior that's inside of that? And the work I'll describe is work that kind of originated with a really terrific graduate student, Zara Kadkodai, and another student, Shreyas Mohan, another fantastic student also from data science. They're both in the data science program at NYU. And my colleague, Carlos Fernandez-Granda. That's where the work originated. We were studying these networks and trying to understand what it is they're doing. And we arrived at some conclusions that they, first of all, that you could at least approximately describe them as projecting things onto low-dimensional spaces. Those we could calculate what the dimensionalities of those spaces are and how they varied with noise levels. We could calculate a little bit about the geometry and arrangement of those spaces. They sort of, at least locally, they look like they're some sort of low-dimensional manifold, some sort of curved space. So we think that, at least conceptually, what these things are doing is projecting onto a low-dimensional manifold, which is adaptive. It's different. It's completely different in different parts of the space. So that's still a somewhat vague description of what's going on, and it's very difficult to pinpoint precisely how and where that happens. In any case, I'm going to charge ahead. So our goal then is to somehow pull the prior out of this and make use of it, and then use that prior to solve other problems. This is not the first time people have thought that you could take a denoiser and get the prior out of it and use it to solve other problems. And in fact, there's a history of this idea, which kind of falls in different communities or sub-communities and goes under different labels. The earliest thing, I think, is probably this work on plug and play, which is from the signal processing community. Charlie Bauman and colleagues developed this idea ages ago, where they took they used an ADMM, basically, algorithm to decouple the optimization problem, and they plugged a denoiser in for the proximal step. And so there's something a little bit strange and approximate about that, because the proximal step, what you're trying to do is solve for a map estimate, but you're plugging in something that's minimizing squared error. So it's not the maximum, it's computing the mean. So there's something a little bit of a mismatch in the use of this, but the idea of taking a denoiser and using it to solve other problems, I think is really important. And I sort of see that as one of the first places where this shows up. In the machine learning community, you see these ideas on denoising score matching that Yoshua Bengio and Pascal Vincent and others have developed, along also Aapo Hyvarinen. So there's a whole set of work that kind of emerged from that community, completely different and often not even seeming to be aware of the work that had been done in the signal processing community. And most recently, there's all this work on diffusion-based generative models. It really starts with Yasha Soldikstein. And that work has exploded. You read about it in the newspaper, basically. The diffusion models are the things that are responsible for DALL-E and Imagen and Midjourney and all of these fancy things that are happening at Google and Facebook and elsewhere to generate very high-quality large images. Okay, so when we started working on this, it was like 2019 or so, and the three things that inspired us, or late 2018, I guess, the three things that inspired us were this plug-and-play work by Zhang and these pieces of work by Song and Ehrman and Guo and colleagues. And Zara and I started thinking about how can we make use of denoisers and really do something more correct to pull the prior out. And what we arrived at is a very simple formulation, which I'll just walk you through quickly because it's so easy to see where it comes from. So the mean squared, this MMSE estimator, the thing that's minimizing squared errors, computing the conditional mean, there's the conditional mean, the expected value of x given y, which we think of as an integral, a very large integral. And so you can convert that into a more usable form where you can access the prior. So here's the idea. The prior predictive density is the distribution of the noisy data. So think of that as like a blurred version of the prior. Actually, you can see it here. So that you write this out as the integral over the joint, marginalize the joint distribution. Since the noise distribution is Gaussian, we have a Gaussian here convolved with the prior, p of x. And so this is just a blurred version of the prior. Take the prior and blur it by an amount that's appropriate for the noise level. That's what sigma is expressing. Okay, so that's p of y. And now differentiate, take the gradient of p of y, divide it by p of y, multiply by sigma squared. I'm walking through this quickly because the derivation is pretty simple and you can read about it. And this gives you an absolutely amazing result. When I first encountered this, it was a student of mine about 12 years ago, came into my office and told me this, and I didn't believe him. I told him, I said, that doesn't make any sense. It's really weird. Why would you write the estimate of the image as take the noisy example and just add to it something which is a gradient of the log of the noisy distribution? This probability is the noisy distribution, the prior predictive density. This is very strange because we started out saying that this needed to be computed with it as an integral over a posterior, but it's no longer a posterior, it's just the blurred version of the prior, and it's no longer an integral, it's now a gradient. It's really quite remarkable. This is not a new result. So it turns out that my student, Martin Raffan, who was a fantastic math student, did his PhD in my group, we went off and we did a bunch of reading, started talking to people, ended up talking to David Donahoe, who pointed us to quite some literature on empirical Bayesian estimation and formulations of problems. And it turns out that you can, that this was in the literature. It's often attributed to Tweedy, but the only written example that we found was this 1961 paper by Miyazawa. So this result, which is very simple to derive, but kind of shocking and strange looking, as most of the results in empirical Bayes work are, tells you this is exactly equivalent. This is not an approximation. It's exactly equivalent to that MMSE estimator, assuming that you've got Gaussian noise and you're trying to minimize squared error, right? So it is suggestive of gradient ascent, but this is not an iterative procedure. This is a one-shot denoising estimate. You take one step, done. That's it. One gradient step. And the prior is implicit in here. It's not actually the prior. This is the blurred version of the prior, p of y. So this is basically saying go uphill on this density, on the log of this density, and so now this gives us a route to interpreting what this deep net is doing. So I train the deep net with regression to solve this problem of mapping images to images, noisy images to clean images. Now we're going to take that, we're going to assume that it's doing this, and we're going to use that to gradient descend and try to find samples from the prior. So the algorithm, oh, and I guess I should mention, so Martin in his thesis developed many, many other generalizations of this. It's also related to Shor. Some of you may know that. The Stein's unbiased risk estimate is a way of writing the squared error without actually writing down, without including the prior explicitly. So this is closely related to that, and in fact, they're interchangeable. You can derive one from the other and vice versa. And you can generalize it to many other noisy measurement processes. So there's really, I think, a whole rich set of possibilities here in the era of machine learning to use these empirical Bayes notions, which come from the 1950s and 60s, and bring them forward into modern computing times and machine learning times. Okay, so we made an algorithm. It's really simple. It basically says, take that denoiser defined gradient that I just told you about, iteratively apply that. Take small steps. Don't take the full denoising step. Take a fraction of it, like 5% of it, a few percent of it, and just do ascent. The idea is that if it's a universal denoiser, it knows how much noise is in the image, so it will take steps that are of appropriate length. So the amazing thing about the algorithm is it's incredibly stable. It's very strongly convergent. It doesn't take very long. And it's adjusting its own step sizes because it knows how to tell how much noise or how much inappropriate content is in the image, and it knows how to move toward, as I described earlier, the manifold of natural images. Okay, so it's basically like a coarse-to-fine optimization because, of course, the idea is that it's following the gradient of the blurred prior, and as it gets closer and closer, the blur gradually is reduced until it lands on the manifold. And I have a little illustration in 2 dimensions. This is the algorithm. It's incredibly simple. You have a denoiser. That's x hat of y. You compute f of y, which is x hat of y minus y. That is, it's the gradient portion of that formula I showed you before. And then you just take steps that are proportional to that. That's the base algorithm. And then there are fancy things you can do to inject noise, and I'll show you in a moment to include constraints. So how does it work? Well, this is just a simulation in 2 dimensions. The idea is that there's a little manifold, a wiggly, curly thing that's lying in this 2D space. And the P of y is the blurred version of that. That's when you add noise to this. You take a sample from that manifold. Imagine you have a uniform density on that manifold. Take a sample, add noise. That's the blurry thing. And then you just follow the gradients. And the little red contour is following those gradients. And you follow these trajectories that take you into the manifold, and they land after, sort of 40, 50 steps. Basically, they land on the manifold. So you get samples of the manifold just by starting with something very noisy and taking these gradient steps. Okay. And you get pretty good diversity. Notice also that even in this simulation, you get into these, you actually do quite well getting inside of these little ripples and wiggles of the manifold. If it's tightly curved, you can get in there. And we think that this is true of the manifold of natural images, that it's got lots of curvature, especially in the high frequency details. Lots of curvature. And that makes sense because you want translation invariance. Those are the high frequency details are basically high frequency sinusoids. And if you want translation invariance, you need to be able to capture the little tiny curvature of what happens when you translate a sinusoid of high frequency. Okay, that went really fast, but maybe you have the intuition. You're moving around these little tiny circles as you translate around in the image. Okay, so how does it work? So now let's just try this on images, and you can run this sampler, this iterative sampling scheme, start from noise, generate lots of things. Every sample of white noise gives you a different sample. You get things that look like pieces of images. This is trained on natural images. If you train it on other things like digits, you can get it to generate things that look like digits. And even if you train it on faces, you can get it to generate little faces. And these faces that it generates, if it's trained on faces, are not trained. They're not examples from the training database. They're actually made up. They're mixtures of things that are in the training database, but in ways that are difficult to separate out. So the thing is actually incredibly good at learning and building descriptions of what it has been trained on. Okay, so our interest in all of this was actually not to draw samples from this and look at them and say, wow, they look great. That's a good way to test, but it's not very quantitative. So what we wanted to do is to ask, can we use the prior that we pulled out of this denoiser to solve other inverse problems? We don't want to solve the denoising problem. We already got that. We want to solve other problems, because the problem in the deep net world is that every time you have a new problem to solve, you have to go train a new network. So and we all know, and you've probably all seen, there are plenty of examples where you take basically any problem where you can get enough data, supervised data, and you can train the thing, regression, nonlinear regression, you train it to solve the problem, and then you do fantastically well. So pretty much every inverse problem where you can get data has been solved exceedingly well using these networks. But each one has to be solved anew, and each one needs a new network and a new solution and new training. So what we're interested in here is taking the power, the generality and generalizability of the Bayesian paradigm, but making use of the power of the priors that are embedded in these learned denoisers. So we take that denoiser prior and pull it out and use it to solve other problems. Okay, so it's pretty easy to modify the algorithm I told you about to do this. You just basically build in your constraints. So we started out really simple. We said, imagine we make a linear measurement. It's a low-dimensional measurement, low-rank matrix. And I want to now sample not from the general distribution P of X, but I want to sample from the conditional distribution P of Y given this measurement. Okay, so I'm going to basically modify the algorithm. It's a pretty small modification, but really all it means is you partition your steps into these two orthogonal pieces, one which is lying in the space of the measurements, and one which is lying in the complementary space, in a nutshell. So you just take gradient steps again, using the denoiser for the part that's complementary to the measurement space, using the measurements to sort of impose the desired properties that came out of the measurements, and you can solve lots of inverse problems. So here's the picture, the diagram back to that little 1D manifold. Here's your constraint, your 1D linear measurement, and now you run this simulated algorithm and you land at places that are at the intersection of the 1D measurement and the prior manifold. So you get samples that are drawn from these locations. Notice that the solution's stochastic. So when you run this, starting from arbitrary starting points, you land in different places along here that are the intersections of the two things. Okay, so now let's do it for images, and I'll just show you some quick examples. So here's Inpainting. Here's an original image. There's a box taken out of it. Here's 3 examples. I told you it's stochastic, so each time you run it, you get a different answer. Here's 3 different answers that are all attempting to fill in that black square in the middle with something that's reasonable given what's around it. And they all look pretty good. None of them are matched to the original, but all of them are pretty reasonable as things that get filled in given that surrounding information. And here's some more examples just to give you an idea that it doesn't just work on this kind of almost black and white image. Here's some tiger stripes. Here's things with texture in them. It works pretty well. Here's things with pretty striking visual patterns that it manages to complete. So this is really good. It's like Adobe's Photoshop, the healing brush. But this is, again, this is not trained to solve this problem. We're taking the denoiser and using it to solve this problem. Right? So that's, again, the key point here is to take the prior out of the denoiser and use it to solve other problems. Okay, so that's one. Here's another one, missing pixels. So just drop 90% of the pixels in these images at the top and reconstruct them. That's what's shown at the bottom. The results they look great. You can see there's some missing detail, but there's a shocking amount of sharpness and detail that manages to get repopulated even with that very, very sparse amount of information. In particular, things like the fur on this mandrill actually look pretty good, even though there's very little information about what the content is. Here's another example, super resolution. So these are 4x4 block averages. And what you can see is, so here's 2 other methods that are using deep nets, particularly aimed at solving this problem. And you can see that the results on the right, which are the ones that came out of our network, are actually remarkably sharp and clean and manage to avoid things like aliasing. So here's an example where you have very fine stripes at a sharp angle. And the low resolution version, which is just block averaged 4x4 pixels, is very aliased. You can see that each of these nice straight clean lines is turned into this sort of jagged structure that comes from the sampling. And that jagged structure is somehow manages to survive through these reconstructions, but this method that I'm telling you about manages to see past that and to recreate reasonably straight, clean contours. So I think it's remarkable visually. And one more example, compressive sensing. So now I'm going to do random projections, 10% the size of the number of pixels. And this is, again, a deep net solution that you can find in the literature. And I think the results that come out of this network are significantly better. Again, I just want to point out, all of these examples I just showed you, same algorithm, exactly the same network. The only difference, there's two networks. One is color and one was black and white. I kind of skipped past that, but there's no reason why you can't do this in color. So we built two different networks. They're both trained on large databases to do denoising, and we're using those networks to solve all of these problems. We just have to specify what the measurements are, and then we can solve any of these problems. Same algorithm. Okay. And numerically, it holds up pretty well, too. So this is a comparison to for the super resolution with a couple of other methods that are also using deep neural networks. And the thing that's kind of interesting here is that the PSNR of this is a little bit worse than these other specialized methods, but these are samples, right? So if you run it 20 times, and you think of those as samples of the posterior, if you average the samples, you actually get something that's, if those really are samples of the posterior, the average of those samples should be close to the mean of the posterior, which is the thing that minimizes the squared error. And in fact, when you do this, you get results that are better numerically. They're slightly blurrier. They don't look as good, but they're better numerically. And so, on the right is what you get when you average over, I think we did 10 or 20 samples, and the results are a little bit better. In terms of the mean squared error. It also runs very fast. So I told you before, the number of iterations could be on the order of 40 or 50, and you can get good results out of that. Okay, so numerically it works great. So the last thing I want to tell you about is the thing that we're doing with Stefan and with Florentin, who's sitting over there, and Zara, who's not here. She couldn't get her visa in time, so she's not here for the meeting. So the global structure that I told you about, that this thing can learn, like the faces and the numbers, it works great, but it relies on the network having a global receptive field. That is, the output of any one of the pixels over here is actually a function of the entire image. If you trace through the network, through all those convolutions, and you ask, what's the impact, where does the input come from to generate this one output pixel, the answer is global. So we call that the receptive field of the model, mimicking the physiology term. And these things are using global receptive fields. And it turns out that if you train exactly the same network, but where the receptive field is not global, so the receptive field here is a little small patch like this, you train the same network with the same architecture to denoise these images, and now you try to synthesize, run it through the iterative algorithm to synthesize. It doesn't make faces. It makes textures. It makes things that are, it's basically like a Markov model. It's treating these things as if they have some statistical properties locally, and those do not chain along properly to give you a global structure that you have in this face. Okay, so how do we fix that? Or you might be wondering, how is it that DALL-E and Midjourney and Imagen and all those fancy things that I keep reading about in the newspaper that generate nice big images, how do they work? And the answer is they are just huge. They make absolutely huge networks with often billions of parameters. Our network is tiny compared to that. And they have global receptive fields that cover the whole image, 1,000 by 1,000, 1,500 by 1,500, whatever the image size is. They have huge receptive fields. So our question was, well, how do we fix this? We don't want to make the network bigger, so how about if we make the image smaller? And of course, this is going to be a multi-scale story because it's involved, it's a collaboration with Stefan. So take this image, make it smaller, and now we can use a smaller network. But of course, we lost a lot of information when we made it smaller, so we want to keep around some other information, like, for example, wavelet subbands. So we can take this now and partition it using an orthogonal wavelet decomposition into 4 subbands. You can think of this as the low resolution version, and then these 3 detail images, which are labeled with a bar over top. Okay? So now I can write the joint distribution of x naught, the full image, as a distribution of this low-res thing and these 3 things packed together, which I'm calling x bar. And of course, I can rewrite that with Bayes' rule so that it's conditional. So now I've pulled out the p of x1 separately, so now I can think about building that model using a smaller network. And I can think about this conditional thing. And one more piece, which is we want this conditional thing, we're going to assert and then test that this piece can be done locally. It doesn't need to be global. In particular, little tiny regions of this can be used to condition these three pieces, and that would be, and the question is, how local can we make it? Right? We can assert it and we can try it, but the question is, how local can we make it and still get a good result, get a good description of the probabilities? And the answer is surprisingly local. Oh, and of course this can be cascaded. If that image here wasn't small enough, you have a really small network and you don't want to use an image that big, do it a few more times, build a wavelet pyramid, a multi-scale cascade, assume all of these are local and Markov, and there's a product of these, of course, for each of these, and then there's one little tiny low-pass residual at the end that you have to build a global model for. Okay, so I wouldn't be telling you about it if it didn't work, and it does work. This is the architecture that imposes all of that. I'm not going to spend time on this because I'm out of time. So this thing is basically we're going to train this thing to denoise. It's going to have conditional convolutional neural networks and one base convolutional neural network. So this one is the one that operates on the low-pass residual. These are all conditional, operating locally on those subbands. Put all that together, train it all jointly and simultaneously, because that's the way we do things in the machine learning world, I'm told. So we just train the entire thing, one big bang on tons of data, and it works. And so let's see how small can we make those neighborhoods. And the answer is, if we were just doing denoising and we were doing it flat the way we started, the performance falls. This is input PSNR and output PSNR. The performance falls as you make the neighborhoods smaller. So the smaller the receptive fields, the more the performance drops. Over here in the multi-scale version, remarkably, this is the size of the receptive fields for those local conditional calculations. As these things drop, you see almost no performance drop until the very end. The 5 by 5 neighborhood is a little too small. 9 by 9 seems to be basically the same performance as all the others. So you can make these quite local. 9 by 9 is like 1% of the image back in the full-size image. So this is a very small receptive field that is sufficient to capture the denoising performance over the whole range of noise that we've got here, which is pretty broad. Okay, and just so you can see it, and then I'll finish. This is what I showed you before. If you try to do this with a flat denoiser, you get something with small receptive fields, you get something that looks like texture. If you do it with the iterative algorithm, you can generate faces again. Okay, so I just want to thank the people that were involved in the work. Zara and Florentin were involved in all of this recent work, and that's going to be presented at ICLR in a week and a half, I think, at the meeting. And the earlier work studying the denoisers was also involving Sreyas and Carlos. And I want to thank Stefan. There's a picture from Germany a bunch of years ago, about 10 years ago, at a computer vision summer school that involved people thinking about human vision and perception and neurobiology and signal processing and machine learning and computer vision and all of the above, and harmonic analysis. And Stefan, as usual, everybody wanted to talk to Stefan, because Stefan has, as was already said by Shihab earlier, Stefan really unifies a lot of different communities. He has really a deep appreciation and a belief that all of these different approaches, they're different and they use different languages, but there's a common set of core themes that are very beautiful and that interact across them. And I think I don't know anybody else that manages to bridge and connect to all of those things so nicely and so in such an accepting and lovely way. So thank you for that. It's really wonderful. And I wanted to get you a gift. And I looked online to try to find the right gift for Stefan, and I found this, and I thought it was perfect. Unfortunately, the company's out of business. So I guess they didn't sell too many of them, of this wavelet signal processing for high-end audio. So I guess maybe this is not a good application for wavelets. Okay, thank you.
I guess we are super late, but maybe one question or one comment. Maybe from Stefan or from someone else.
First of all, thanks for this beautiful talk, and maybe that's a way to show that ideas disappear and something else comes in. So, too bad I won't have it. I wanted still to have a question. Behind all what you showed, which is amazing, you showed these pictures in 2 dimensions. But the real surprise is that in very high dimension, we can estimate the score, this gradient of log p. Nobody imagined 1 second that one could do it. So given all your experience about all this, why do you think it works? How come we can estimate this gradient log p of x in very high dimension? Do you have any idea?
I agree that to me, the shocking thing about this, and perhaps to you as well, is that we all thought the cursive dimensionality meant that you really can't learn probability distributions in million-dimensional spaces, so we had given up on this a long time ago. And along comes these new ideas, and some of it is still, so why does it work? Why is it possible now to do this when we thought it was impossible for the last couple hundred years? I think the only answer I can give is, one, the problem is remarkably reduced and simplified by forcing the structure of convolutions and simple rectifiers. So the nonlinear structures and in that cascade are very, very simple and very constrained. Two, it's not training a probability, it's training a mapping, and I think that's easier. Doing regression to learn a mapping from a noisy thing to a clean thing. So you're taking things that are the clean things and you're just perturbing them a bit and you're learning how to push them back onto the surface. And that seems to be a much easier problem than learning a density, a scalar function on the entire space. So I don't, other than that, as you know, we've been talking a lot, Stefan and I, with our students, about how it is that these networks can generalize and when do they generalize? How much data do they actually need to start bridging the gap between the training examples and doing something that's more general and that applies to new test images? And the answer there, I think, is still unclear. Stay tuned next year. Stefan is going to tell you the answer next year.